Hi all, welcome back to the second part of the lecture of today. Thank you to Christina for teaching us all this nice stuff. Christina, the space is yours.
Thank you. Okay, then we will continue with what we were talking about. In the last part of the previous part of the lecture, I show you this slide just to introduce what I'm gonna talk right now. I already summarized some of the most important results of clustering measurements in optical wavelengths for different kind of population. I show you how clustering depends on different properties of the sources, and I also show you the clustering of other populations that we can detect at higher redshifts. Then in this part of the lecture, I'm going to focus more on the populations that we can detect at other wavelengths. I already mentioned that we can detect other different sources in infrared, submillimeter wavelengths, and radio wavelengths. I will be focused more on radio and submillimeter wavelengths. Then I'm not going to talk about infrared here or X-ray or other part of the electromagnetic spectrum. Okay, so I'm gonna start with radio wavelengths, just because we have more availability of surveys right now at radio wavelengths. In this plot, I'm showing different surveys that has been performed at radio wavelengths. Here I'm showing the frequency in which the surveys have been performed, because radio wavelengths, all of this is radio, but you can go to lower or higher frequency within the radio regime. And we have several surveys across this wide range of frequency. Then this is showing the sensitivity, then how deep the survey is, and the size of the circles are showing the resolution of the survey. Then for clustering measurements, we are interested in both in sensitivity and in resolution, because we need a relatively good resolution to really resolve the objects and obtain a precise position of the objects in the sky. Then, for example, some surveys with 25 arc seconds of resolution maybe are not adequate to perform clustering measurements. And we also are interested in sensitivity, because as long as we go deeper, we can detect more sources, and specifically we can detect more faint sources. And we can also go to higher redshifts. Then this is just a summary to show some of the surveys. Then we have VLA, which is very known. We have FIRST, which also used VLA, and VSS. And particularly, I'm working now with LOFAR surveys, which are those shown in red here. LOFAR is a survey at lower frequencies than most of the surveys, and it's gonna be very promising in the few next years. At radio wavelengths, we have much more coverage in area than at submillimeter, for example. Then we can perform some clustering measurements, and people have been doing this from several years ago already. We still lack of precise redshifts, because when you detect sources in the radio sky, you normally don't have redshift, and to obtain the redshift, you need a multi-wavelength information in the same sky region to really obtain at least photometric redshift of the sources. Then this procedure is a little bit different than in optical and at low redshift, because in this case we have to look for the counterpart of the source at other wavelengths and then check what is the redshift of the source. And normally that is done using CD fitting or other techniques. Then to really obtain redshift of the sources, we need to explore a region of the sky in which we have also information at other wavelengths. This is an important point. When we observe at radio wavelengths, we are mostly detecting two different populations, basically AGNs and star-forming galaxies. I guess most of you knows what are AGNs. Otherwise, well, I can show you this here. I already explained you what is a quasar. Quasar is one type of AGN, but the AGN population is larger than just quasars. AGN are also active galactic nucleus as the one I show here, but depending on how you observe this AGN, in which direction, you will detect this as a quasar or as a radio galaxy or as a Seyfert galaxy or other different type of objects. Then you can think that AGNs are these extreme objects too, but if you look at this from this angle or from this angle or from this angle, you will detect this as a different object. Okay. But keep in mind that at radio wavelengths, we can detect mostly AGN and star-forming galaxies. Well, first is one of the first surveys performed at radio wavelengths in the sky. This is at 20 centimeters. This is a survey covering 10,000 square degrees. Then it's a pretty large area. This is just showing the sky coverage of the first survey. And different colors is just what has been added different years. Then this is a very important survey, like a pioneer survey in which cluster measurement has been done. And I already mentioned about LOFAR. LOFAR is an instrument, a radio telescope installed here in the Netherlands. Then actually here in the observatory, there is a very big group working with LOFAR data. This is observing at lower frequencies than other surveys and than first surveys, for example. And here I'm showing the sky coverage of LOFAR. Then in the future, we will be covering all the northern hemisphere. Then we are really covering very large areas in the sky. This will provide a lot of very nice data and unprecedented catalog of sources in the radio sky. Here in green is the data that is already public in the data release 1. The red and yellow points are data that is already observed, but it's not public yet. But it's available for people working in the LOFAR collaboration. Will be public relatively soon. And the black points are showing the areas that are planning to be observed, but has not been observed yet. Just for a comparison, the size of the first surveys is more or less the yellow part here, but also is extending a little bit more in declination here. But then LOFAR is increasing a lot the area in which we are making the surveys. This is one work from Overseer et al. 2003. They used data from the first survey and the NVSS to measure the angular correlation function for sources detected at radio wavelengths. As I said, normally at radio wavelengths, we don't have redshift information, unless we have multi-wavelength coverage. Then that was not the case for this survey. Then they only had 2D positions of sources in the sky. And they measure the angular correlation function, and then using the Lindbergh equation, they obtain the R0 parameter. They measure the clustering for different subsamples based on the flux density of the subsample. Then here we have fainter samples, and here are the brightest one. And what they detect is an R0 value around 5 megaparsec over H. Then it's not very different that the previous value that we have been talking about. But they also find that at higher fluxes, they have an important increase of the clustering for the sources. Then the interpretation of this is that the faint part of the population is more dominated by not so powerful radio galaxies, and this part, the bright part, is more dominated by the more powerful radio galaxies. Oops. And to explain better this is one example of a radio galaxy. A radio galaxy is also a type of AGN. Then you have the AGN here, and you normally have 2 big jets. But for the case of the not so strong population, you have that most of the emission is close to the center of the AGN, and at the end of the jets, the emission is not that strong. But on the other hand, in this case, when the population of bright sources is more dominated by this kind of objects, in which you have the AGN here, and the jets are very luminous, like in the edge of the jet. Then this kind of sources are more powerful, and then the interpretation of this increase of the correlation function is because here you are more dominated by this kind of radio galaxies, and therefore this means that these powerful radio galaxies, which are called FR2, these are FR1 and this is FR2, just definition based on how are the jets. This kind of galaxies should prove much more massive structure compared with the structures proved by this kind of galaxies. This is more or less at redshift 1. The average of the redshift of the sample is more or less redshift 1. And this result also is consistent with other results that has been found at higher redshift, like redshift 2 or 3, in which radio galaxies are found to be hosted by very massive dark matter halos. Also, here I'm going to show you a result of another work. This is also clustering of radio sources, but in this case, they are using the VLA Cosmos project. Then this is a much smaller survey, then only cover 2 square degrees, and still contain a very large number of objects. But the nice part here is that they have multi-wavelength information. Then they have more information to split the sample based on their different properties. Then specifically, they can actually split the radio sources between star-forming galaxies and AGNs, and then they can measure the clustering of these 2 different populations. In the measurement that I showed before, they didn't split the sample like this, then you were just looking the clustering of all the objects together. But as I will show here, star-forming galaxies could have very different clustering than AGN, and then it's very important that we can split the sample in the different populations. Then here, they measure the angular correlation function of around 2,000 star-forming galaxies, a redshift lower than 1. You can see here the measurement. they estimate a correlation length of 5 megaparsec over H. And here in the right, you can see the clustering of around 1,000 AGNs, a redshift lower than 1. They measure much more strong clustering in this case, then they measure an R0 of 6.9 megaparsec over H. This is work from Halital 2018, then it's a very recent result. And the main point here is that AGNs are much more strongly clustered than star-forming galaxies, which imply that AGN are hosted by more massive halos than star-forming galaxies. That is actually not very surprising, but it's nice that we can measure this. Here, the AGN population is including all type of AGN, then radio galaxies, quasar, everything. Then hopefully in the future, when we have more large surveys, we can also split the AGN population in the different types of AGN, which could have also very different clustering. Because when you put everything together, you could be diluting the clustering of some objects. For example, if quasar has a clustering very different than C4 galaxies or other type of AGN, you will be averaging all the clustering signal for all the objects here. Then that will be nice to make in the future. And here I'm just showing the evolution of the R0 parameter for star-forming galaxies and AGN. Also, here I'm showing, this is a plot from Halital 2018 too, and they are showing just a summary of the previous from different studies for star-forming galaxies at different redshifts. This also includes, I think, some optical measurements, and it's not only radio measurements. And here the one for AGN over redshift range between 0 and almost 2. Then the main point is that in general, star-forming galaxies are less clustered than AGN. You can see that here they are proving correlation lengths between 2 and 6, more or less. But for AGN, you are proving more close to 6 and 7 megaparsec over H in general. But still, we have a lot of scattering between the different works. The error bars in the measurement are still important. Then we really need larger surveys to constrain better the clustering of radio sources. And in that sense, LOFAR and SCA that is coming also will make a huge progress. Okay, and finally, for today, I'm going to talk a little bit about sub-millimeter wavelengths. These are probably the wavelengths at which we have less availability of surveys. Normally, we have small surveys at these wavelengths and with low resolution, because most of the surveys are performed with single dish telescopes, then which provide low resolution in general. Then, for example, this is one survey which is called LES survey. Is performed with an instrument called La Boca in Apex in Chile. And this was done in 2009. And over this survey, which covered 0.25 square degrees, there were 126 sub-millimeter galaxies on this survey. Then we are talking about much lower number of objects in this case. Another survey, which is the larger survey performed so far at sub-millimeter wavelengths, or in particular at 50 micrometers, was published on 2017. Is performed using SCUBA 2, and this covered around 5 square degrees. contains around 3,000 submillimeter galaxies. The nice part of this survey is that it's covering some regions in the sky in which we have a multi-wavelength information. Also, in this case, this survey is also covering the SCDF, which is also very known field, and we also have multi-wavelength information. And that is actually the only way to do this at 2-millimeter galaxies, because the sparse of the samples, we really need most information, the more information possible. The multi-wavelength information is very nice, and also because at 2-millimeter wavelengths, we are sensitive to detect objects over a very wide redshift range between 0 and 10, because at these wavelengths, maybe you have heard about the negative K correction, which means that the flux at this wavelengths is not decreasing with the distance as happen in all the other wavelengths. But in this case, we are equally sensitive to detect sources over the entire redshift range, basically between 1 and 8. Then we really need to constrain better the parameters of the sources, and we need multi-wavelength information. So at 2-millimeter galaxies, the population that we can detect are the sub-millimeter galaxies. This is a population of dusty galaxies that has a strong emission in sub-millimeter wavelengths. And the reason of that is that they have a high star formation rate, and they have a strong UV radiation from a star in those galaxies, and this radiation is absorbed by the dust in the galaxy, and the dust re-emit this energy at sub-millimeter wavelengths. Then that is the reason why they are so bright at sub-millimeter wavelengths. And then in general, they are very luminous sources. They are very massive, have a high stellar masses, are star forming. They have high star formation rates, around 100 to 1,000 solar masses per year. Then it's a really high star formation rate, and also they have the peak at redshift between 2.2 and 2.5. Then most of the SMGs are actually, by definition, located at high redshift. And here I'm just showing some example of sub-millimeter galaxies detected with ALMA that you can see here in the green contours. Okay, so in 2017, Wilkinson et al. Measured the angular correlation function of sub-millimeter galaxies using a sample of 300, more or less, sub-millimeter galaxies from using SCUBA 2. Here I say they measure the angular cross correlation, because given that they have a small sample size, they are using a cross correlation technique to decrease the error bars of the measurement. This is something that I mentioned yesterday, that is you can use a cross correlation with a large sample of other galaxies to decrease the uncertainties in your measurement. Then that is a technique that they are using, but at the end they can obtain the correlation length of sub-millimeter galaxies. They obtain a value of 4.1 for sources between 1 and 3. They also split the sample at different redshift beams. Here I'm showing the different redshift beams between 1 and 3.5. You can see that they don't have so much galaxies per beam, but they still make the attempt to measure the clustering. And they find a tentative evidence in which the correlation length is increasing at higher redshift, and strongly increasing at higher redshift. But still, this measurement is still dominated by large uncertainties, as you can see here in the error of the R0 parameter. Also, this is well related with the question that I received in the last part of the lecture. Someone asked about how blended sources impact the clustering measurements, and this is something actually very important because this survey here is what I showed before, is the LESS survey performed with APEX with a angular resolution of around 20 arcsecond. Then here I'm showing the projected correlation function measured using this data here, the 126 SMGs detector here. This was measured by Hickox et al. 2012. And they measure, again, using a cross-correlation technique, they measure the clustering of submillimeter galaxies, and they claim that the halo mass in which submillimeter galaxies will inhabit is close to 10 to the 13 solar masses. Then they claim a very strong clustering for SMGs. However, as I'm showing here, ALMA and other interferometric follow-up of submillimeter sources revealed that several of the sources detected in this kind of surveys with single dish and with low resolution are actually composed by several SMGs. Then, for example, this single source here is actually composed by 3 fainter sources. And this is just because the angular resolution that you are using. ALMA has an angular resolution around 1 arcsecond, then we can really detect and resolve the sources. But single dish data have a much worse resolution. Then using this new information with more precise positions and also using some redshift for these galaxies, I was working this year in the measurement of the clustering of submillimeter galaxies, and we actually found that the clustering was previously strongly overestimated, just because this effect of blending and resolution, and we are actually computing halo masses which are almost 4 times less massive than previous estimation. Then this is just a recent result. Then the clustering of submillimeter galaxies is still controversial, and we really need more larger surveys. This measurement here that I did was made with around 50 galaxies. That is not a very big sample, but it still is revealing very nice results. Then I'm gonna summarize a little bit here. This is my last slide. This is showing the correlation length as a function of redshift. Here I'm showing everything below redshift 1. What I have said so far is that we can distinguish different clustering based on the properties of galaxies. For example, red galaxies have a higher clustering compared with blue galaxies. We find that those are also red galaxies, but are much more luminous red galaxies, have a higher redshift than normal red galaxies that are less luminous. In general, galaxy cluster, of course, are the more clustered population in the local universe. Here I'm showing the clustering of AGNs measured from radio surveys. And if we extend this to higher redshifts, this is more or less what we have. Quasars have been shown to increase strongly the clustering at high redshift, like going in this direction. I show you that Lyman break galaxies, which are the light blue color here, have a more or less flat correlation length at redshift 3, 4, and 5. and their correlation length is not so different than star-forming galaxies in the local universe. I also show you that in the case of submillimeter galaxies, we have this measurement based on single dish telescopes, but this measurement could be strongly overestimated, and maybe this point here is more precise for their clustering, but still we need more constraint. And there is a tentative evidence that this clustering should evolve with redshift 2, similar as the quasar, but it's still not very clear. Then yes, this is more or less the summary of what we have been talking today. You can see that the clustering dependency of properties is a very complex thing. Every population has different kind of clustering. Then in the next class, we will talk about how can we interpret all those results, what doesn't mean, what means that we have a higher or lower R naught at a different redshifts, and how can we get some conclusions about galaxy evolution, for example, or if we can use this information to make evolutionary links between different populations. Then I'm going to be talking about that tomorrow. And that is everything for now. And now I have a Kahoot with some questions. Then I hope you can join and play with me. There's no questions so far. Okay. Okay, so this is the game pin. Then I invite you to join us and play and reply some questions. I'm going to give you a couple of minutes to join. As yesterday, the time for each question is 60 seconds. Then it is less than the first day. And I think you received the signal like 20 seconds after me. Then you have 40 seconds actually to answer the question. Okay, I think there's not more people joining. We just wait a little bit more. Okay, I think that it's, then I'm gonna start. Okay, then the first question, the Sloan Sky Digital Survey covers an area of between 1,000 and 10,000 square degrees, between 10,000 and 20,000 square degrees, between 20,000 and 30,000 square degrees, or between 30,000 and 40,000 square degrees. Okay, not all of you answered the question. Then it was a hard one, but yeah, the right answer is this one. Actually, Sloan covered around 15,000 square degrees. Okay, great. Let's go with the next one. This is a true or false question. More luminous galaxies reside in more massive dark matter halos than less luminous galaxies. True or false? Okay, this is true. Not all of you were so sure about that, but in general, yes, more luminous galaxies reside in more massive dark matter halos than less luminous galaxies. That is what I show you in the plot of Sehavi at the beginning of the lecture. This is in general at high redshift is not very well constrained, but is the general trend. Okay, question number 3. The clustering of local blue galaxies decreases toward lower luminosities. Why don't we see this trend for red galaxies? Because faint red galaxies are more massive than bright red galaxies, because blue galaxies are more massive than red galaxies, because bright red galaxies are not so abundant, or because faint red galaxies are often found in galaxy clusters. Okay, yeah, most of you replied this correctly. It is because for red galaxies, we see that at the very faint end, red galaxies tend to be more clustered than bright galaxies. And this is just because often faint red galaxies are located in galaxy cluster. Then we are basically measuring the clustering of galaxy cluster, to say in some way, of those very massive dark matter halos. And that is why we detect a higher clustering for faint red galaxies. Okay, question number 4. At a fixed stellar mass, galaxies with higher star formation rate are more clustered than galaxies with lower star formation rate. True or false? Okay, that is false. It is actually in the other way around. I saw that most of you replied this wrongly. But yeah, lately has been discovered that higher star formation rate implies that galaxies inhabit in less massive dark matter halos. Then, yeah, that was false. Okay, question number 5. The clustering of high redshift line member galaxies is similar to the clustering of star-forming galaxies in the local universe. True or false? Wow, 4 and 4. Yeah, that is actually true. The star-forming galaxies in the local universe seems to have similar clustering, specifically similar correlation length than the line member galaxies at high redshifts. Okay, question number 6. In the local universe, which of the following objects have the highest clustering? Red and luminous galaxies, luminous quasars, cluster of galaxies, or submillimeter galaxies? Good. Yeah, the answer is a cluster of galaxies. Cluster of galaxies are the more massive dark matter halos in the local universe, then therefore they have the highest clustering. Submillimeter galaxies are not at the local universe, and red and luminous galaxies have higher clustering than blue galaxies, but it still is lower than cluster or the more brightest galaxies, and luminous quasars have a relatively flat and low clustering at low redshift, at least. Okay. This is a true or false question. At high redshift, quasars are the most clustered population in the universe. True or false? Wow, okay. You didn't got that, I think, but that is true. Quasars are so far the most cluster population in the early universe. I mentioned actually that the correlation length is around 24 megaparsec over H, which is much more, much higher than all the other objects. Okay, question number 8. When we measure the clustering of sources detected in radio surveys, we are actually measuring the clustering of AGNs and radio galaxies, AGNs and star-forming galaxies, AGNs and submillimeter galaxies, or star-forming galaxies and quasars. Okay. Yeah, the answer is AGNs and star-forming galaxies. That is the correct one. I see that several of you, well, not 2 people, answer AGNs and radio galaxy, and 2 people AGN and submillimeter galaxies. And then at radio wavelengths, we don't detect the submillimeter galaxies. We detect those at submillimeter wavelengths. And the first one, AGNs and radio galaxies, no, because radio galaxies is just one type of AGNs. Then the complete population that we can observe at radio wavelengths are AGNs, including radio galaxies, but also star-forming galaxies. Okay, this is a true or false question. If the correlation length of a population increases with redshift, this means that the population inhabit more massive halos at higher redshift. True or false? Okay, the answer is false, and I see that most of you reply true. And well, to be honest, this is a tricky question, and we will cover this more in detail tomorrow. But I would like you to keep in mind that R naught, or the correlation length, is an indicator of the halo mass in which objects inhabit. But for a fixed redshift, we can say that a higher R naught means more massive dark matter halos, but it's not that simple to compare R naught at different redshifts, and the trend is not necessarily always that we will have a higher dark matter halo for higher R naught values. We only can say here that if the population has a higher R naught value at higher redshift, then the population is more strongly clustered, but we cannot translate that into mass like that easily. We only can do that if we work at the same redshift. but not a different redshift. Oops. Okay, and then last question. The largest area that has been covered by a survey at sub-millimeter wavelengths at 850 micrometers is lower than 1 square degree, lower than 6 square degrees, lower than 8 square degrees, or lower than 12 square degrees. Good. The answer is less than 6 square degrees, and the size is exactly 5 square degrees. Then, as you can see, we are still very behind in sub-millimeter wavelengths compared with what we have been covered with Sloan, for example, at optical wavelengths, which is 15,000 square degrees. Then still so much work to do here. Okay. Let's see who won. Vanessa, great, congratulations. You were the winner, and also nice that Carbine Nemesis were doing good also. Okay, cool. Okay, then I think that is everything for today. I will just leave you with my last slide, the take-home message. I am just like repeating the most important point that I mentioned today. We need large surveys to perform accurate measurement of clustering, even when small surveys also can help us. And we still can measure something. I talk about the dependency of different parameters with the clustering. I also talk about the clustering at a higher redshift for different populations. And this point is important against of intuitive expectation in which clustering will increase with time because structures are more are growing over time. We observe that some populations are equally clustered over long times, like, for example, light membrane galaxies, and some of them decrease their clustering with time. For example, quasars has a much stronger clustering at earlier times compared with later times. Also, this message is like a general message that cluster measurements of different populations and at different wavelengths may provide a complete understanding of galaxy evolution because we can relate some different populations detected at different wavelengths. And tomorrow we are gonna talk about some physics behind this, and I will tell you how can we interpret all those results, specifically how can we understand that some populations have higher clustering at higher redshifts, which is not so intuitive. Also, I'm gonna tell you how can we put all this information together to really understand galaxy evolution in general. Then I hope you can join us tomorrow. For today, I want to stop sharing. For today, I think that Esteban sent an email with the workshop for the afternoon, and I also uploaded the workshop in my webpage. We're gonna to continue with what we was doing yesterday. Some of you already sent me some plots and your codes, then thank you for that. And I encourage you that other people also can send me some results. And that's it for now.
Thank you very much, Christina, for the lecture of today. I don't see any questions right now in the chat. So I'll guess that people will be either write to you with the questions or will make the questions in a further time because maybe they need to analyze a little bit better all the things that you have taught today.
Yeah.
So thank you very much. It's 10 o'clock, so we should reconvene at 10:25 to start the exercises, the workshop number 3. The workshop number 3 was sent half an hour ago to each one of the emails of the participants. And so thank you very much and see you in 25 minutes.
Yeah, see you.
See you.